So, good morning. Before continuing our lecture, let me share my widescreen. Okay, try to design, in conclusion of our buck boost lecture, buck boost operating in discontinuous conduction mode with these specifications. The input voltage range is from 10 up to 15 volt. The output voltage V0 is negative 15 volt. The maximum output current I know is 1 amp, and the maximum admissible ripple across superimpose onto the output voltage is 100 millivolt. Okay, so design a buck boost DCM. So that means that you should derive the value, okay, the standard value for each of the component in the circuits. Okay, evaluating the stress in order to say buy them. Okay, so continue our discussion about the power flow in electrical networks. Last time I focused my attention on a generic network. This network is not important if it is linear, not linear, time variant, time invariant, or time continuous, etc. Okay, any network can be acceptable for that discussion. This network we can isolate two terminals to which we can have a current I and a voltage V. Suppose that these voltages and currents are, say, periodic and the period is T. Okay, V and I, periodic function, and the period is, let's say, T. I mentioned about the fact that one useful quantity that can be used to analyze the network is the power. Okay, the power which is, for example, the instantaneous power, so the product between the voltage and the current at the input port. Okay, but a more useful quantity is the average power. Okay, the average power is defined in this way. And why it is more useful than the instantaneous power? Because typically, especially in power electronics, in the network, inside the network, we have a lot of reactive elements that stores energy. So if you want, for example, to look what happens at the output port of the same network, okay, the instantaneous power is not something that you can relate at the same time instant with respect to the input power. Okay, while for a lossless network, for example, the output power is always the same, the output average power the same of the input average power. Okay, due to the presence of these reactive elements that release and store energy in a different time interval. So we have to look to this average power, and since V and I at the input port are generic function, periodic function, we can express V and I in terms of Fourier series. So V and I as a summation of V infinite sine waves with different amplitude have different frequencies, and each of these frequencies are integer multipliers of a fundamental one. Okay, the fundamental component is the frequency having, say, frequency f, which is equal 1 over t. So you have harmonics that are n, which is an integer multiplied f, okay, with n that, say, goes from, let's say, minus infinite to plus infinite. Okay, and when you multiply variables, current and voltages, that have different frequency, and then you integrate this multiplication, this product over the same period, then you can get 0. So the power, the output power, the average power, is only due to the product of sinusoidal variables that have the same frequency. Okay, this is what I said last time. So suppose now, just for the example, that the voltage V in that network is a sine wave. For example, this one. Okay, the period is t. While the current is not a sine wave, is again a periodic variable, okay, but is something different. Okay, for example, I don't know, is something which is okay. Suppose that this is something. This is periodic function. Okay, so my drawing is something like this. Okay, is not a sinusoidal waveform, but is periodic with the same period t. We can define the root mean square value of the voltage V, which is 1 over t, the integral over the period t of V square t at t, and this is squared, root squared. Okay. The same we can do for the current IRMS. Okay, same definition. 1 over t, the integral of I square t root squared. The product of these two root mean square value is called the apparent power. Okay, this is the apparent power. As I said before, one of the most useful quantity is the average power. Okay, so let's derive, for example, in this example, the average power due to these two voltage and current waveforms at the input of the network. If you want to consider the average power, you have to multiply the voltage V, which is a sine wave at frequency 1 over t, with the Fourier series, Fourier combination, of all the sine waveforms for each of the frequency, from the fundamental and all the harmonics of the current. Okay, the current is not a sine wave, so I have to say expand in Fourier series. And when I expand this current in Fourier series, I have to understand that the average power is only due, because it's the only product which is give you the integral which is not null, the product of the sine wave of the voltage with the component of the Fourier expansion of the current which has the same frequency. So the fundamental component. So the power, average power, is only due to the product of the voltage V, say, multiplied the contribution of. So let me draw in this way. The power, let me just describe by words. Okay, the power is not null only for the fundamental component of IT. Okay, because this is the variable, the current variable, which has the same frequency of the voltage. Okay, so the power is not only if you, let's say, multiply the voltage with the specific component of the current IT, which has the same frequency, which is the fundamental component of the current. So graphically, This means that the power, this is V T over T having a period T, is given just by a contribution V multiply the current I. Okay, suppose that this is I1. So that means that this is the fundamental contribution. Okay, if you expand the current in Fourier series, it means that you have summations of n, in sine wave n omega t, for example, okay? And then you can have several contributions. When n is equal to 1, so that means that you have the fundamental component, and you have all the harmonics, okay? But all the harmonics have different frequency with respect to the voltage V. So the product that gives you not null average power just given by Vt and the fundamental component of the current. So for example, it's given by this expression. This is just the fundamental component. Okay? So this gives you a not null average power. Okay? So suppose, for example, that you can have this situation. Okay? So Vt is the voltage that you can have at the beginning, and this is the fundamental component. Or maybe you can have another situation, another possible situation, that in which the fundamental component of the current is somewhat larger than that I drew before. For example, it can be something like this. Okay? Again, this is a fundamental component, but say, supposing that my fundamental component has a large peak value, for example, that before. Now, the average power that you can compute by multiplying Vt and I1t, the fundamental component, the blue curve, now is larger than the power that you can have with the, let's say, the red curve here. Okay? Of course, you have to understand that the root mean square value of the fundamental component is lower than the root mean square value of the overall current IT, which is expressed by this voltage waveform here, okay? This current waveform. So, in order to understand which is the ratio between the total possible apparent power, the product of the root mean square value of the voltage and the root mean square value of the current, as I previously defined with the term S, and the power, average power, that you can extract from the circuits, a useful parameter is defined as the ratio between the average power and the apparent power. Or better, average power VRMS IRMS. For example, in these two red and blue situations that I depicted with this draw, this ratio is different. Okay, in the first case, the case with the red fundamental current, which is, say, a small peak value, this ratio gives you a value which is less than the possible ratio that you can have with the situation in which the fundamental component has a larger peak than before. So a measure of the quantity of the average power that you can extract from a, say, possible apparent power is given by this ratio, P over the apparent power, which is called the power factor. So the power factor is a measure of how much average power you can extract from a network that has a specific apparent power. Okay, the apparent power is, let's say, the power given by, let's say, the product of the real waveform you can have at the input. But you know that the average power is only due to product of variables that have the same frequency. So not all the available apparent power can be transformed into a real power, an average power. Okay, so a measure of how much average power, how much real power I can have in a circuit is the ratio between the average power, or the real power, and the apparent power. And this is called the power factor, okay? Of course, it should be useful to have a power factor which is, let's say, close to 1, because this is the maximum possible power they can extract. Typically, this is not so huge in practical circuit, as we learn in a few moments. Before continue, having defined this power factor, suppose what happens to the power factor of sinusoidal signal. So let me compute the power factor of sinusoidal waveform. Suppose, for example, that you have a circuit which is composed by a resistor and an inductor. The classic ohmic inductive load. The voltage V here is a sine wave, okay? And so the current is again a sine wave. For example, you can have the voltage like this, supposing that the period is t. The current is a sine wave, but you have some lag, okay? You have a displacement, you have a something like this, okay? You have a phase which is not null. They are not in phase due to the fact that you have the inductance, you have these reactive elements, okay? But they have the same period. So, which is the average power? The average power is given by definition. The integral of the voltage multiply the current in the t. The voltage is, let's say, Vs sine of 2πft, okay, with no phase. The current has a peak which is Is, sine the same frequency, okay, f is 1 over t, plus the phase theta. If you take the product of the two, you get the average power. So it is 1 over t, then you can have f Vs Is, the integral of sine 2πft that multiplies sine of 2πft plus theta. Now we can use some trigonometric identities. 2πft plus theta can be written as sine 2πft cos theta plus cosine 2πft sine theta. Okay, so you can write in this way this contribution here. So put this trigonometric identity into the integral, so you can have Vs Is over t that multiply the integral of what? And you can have sine that multiplies the sine cosine theta, so sine square 2πft sine theta plus, and here you have sine that multiplies the cosine at the same frequency. Okay, so now you can recognize that this product here, so the sine multiplied the cosine having the same frequency during the integral over the integral 0t is giving you 0. So you just have this contribution here. The integral of the sine square over the integral t gives you exactly t divided by 2. Better. Let me redraw in this way. This is cosine theta okay, so this integral now is t divided by 2. And so the average power is given by Vs Is over 2 cosine theta. So when you have two sine waves and you get the average power, you can recognize that the root mean square value of the voltage is simply Vs over square 2, because this is a sine wave. The same happens for the root mean square value of the current, which is Is over square 2. So this product here, Vs Is multiplied 2, is simply given by VRMS multiplied IRMS. Okay, given VRMS, IRMS for sine waves given by these expressions. So the power is VRMS IRMS multiplied cosine of theta, where theta is the phase shift between the current and the voltage. This quantity, VRMS multiplied the root mean square value of the current, is the apparent power. Okay, so we immediately recognize that P over S, which is the power factor, is given by cosine of theta. So for sine waves, the power factor is given by the cosine of the phase shift between the current and the voltage. What happens? If theta is 0, the power factor is 1. If theta is, I don't know, is b divided by 2, then the power factor is null. So when theta is 0, giving you a power factor which is 1, which means that you can extract the total apparent power as useful real power. Theta equal to 0 means that in our circuits you don't have the inductor. Okay, in that specific situation, the phase difference is null. The current and the voltage are in phase, and so the total average power is equal to the apparent power. This is a total ideal situation in which I have a circuit which is composed by a resistor, okay, giving you no phase shift between the current and the voltage, and so you are able to extract all the apparent power as a useful average real power. Okay, so this can be a very good starting point. Okay, if your circuits, your network that we have in that box at the beginning of the discussion acts as a resistor for the input voltage and current, that in that specific situation your power factor is the maximum which is possible, so it means that you can have all the power available for as a real power. Okay, typically this is not a situation that you can have in power circuits, in power electronics. Okay, because due to the widespreading of nonlinear circuits, for example, of our say converter, in which you have switches, as I described to you before, etc. Say some nonlinear operation, it's difficult to see the network as a real, as an apparent or as a resistor in terms of voltage and current absorbed from the power supply. Remember that in order to make all the electronic circuits to operating correctly, you need DC voltage. Okay, and the first step, for example, in your networks to rectify your circuits, you to put at the very beginning of your mains, which is an alternating sine wave, a rectifier. Okay, and the rectifier is a means by which you can have, let's say, a rectification. So you can have a DC quantity starting from an AC circuit, an AC voltage. Rectifier inside have diodes that are nonlinear element that acts as a switch. Okay, they open. So the typical situation that you can have in all power converters, circuits that, let's say, manage the power in order to make energy conversion, is to have the input voltage, as a sine wave. For example, the voltage that you can have are your electrical mains. Okay, the sine wave. Okay, 220 volt peak value. While the current typically is distorted. We can see later an example of distorted current. Okay, so distorted, what does it mean? That the current, so this is typical in electronics. Distorted means that the current IS, which is drawn by my network S is for source, okay, is not a sine wave as the voltage. Okay, typically the voltage is a sine wave, but the current has a lot of harmonics. Okay, so if the current is distorted and so it has a lot of harmonics, like for example the current I show at the beginning of this class, I can describe in terms of Fourier series. We can have an average value plus a summation of, let's say, infinite terms. For computation here is better you have the cosine. Okay, you can use sine, cosines. Okay, sorry, the sine, as I said before, as I used already before. Okay, sine 2p ft plus, let's say, phi n, which is the phase. Okay, typical situations that in which the average value is null, like for example the waveform I showed you before. At the beginning of this class, I show you exactly the situation I'm talking about here, in which the current is distorted, the voltage is not distorted, the current has an average value which is null. Okay, so I'm putting myself in a, say, in a real practical condition that I can have in real electronic circuits. So this is the expression of the current, which is distorted. So you have a lot of harmonics, the fundamental plus all the harmonics. In order to get the power, the average power, I have to apply the definition. And the definition says that I have to integrate over the period t, the current and the voltage. But remember that this integral is not null only when you multiply components of the voltage and the current that are, say, at the same frequency. So that means that this is given by Vs sine omega t multiply to what? Multiply the here you can have an n here, so it's 2pf tn. If you want, you can scribe as, so it is better with the omega n t. Okay, so the only component in this Fourier expansion of the current that has the same frequency of the voltage Vs is the fundamental component. So when n is equal to 1. So it means I1 sine the omega t plus phi1 now. Fundamental component. But now this kind of computation is exactly the same computation we did before for two signals that are sine waves, okay, like this one. Okay, and the result is given by these results here. So it's the product of the root mean square value multiplied the cosine of the phase shift. So also in this case, we can say that the power is the root mean square value of the voltage Vs multiply the root mean square value now of the fundamental of the current, and then you have cosine of phi1. Rewrite this expression by multiplying the quantity by the root mean square value of the overall current, Is, not just the fundamental component. If I multiply and divide by the Is root mean square value, nothing changes, but I can have, for example, here, this is the apparent power, the product of the root mean square value of the current and the voltages. And here you have another term, which is the ratio between the root mean square value of the fundamental component divided the root mean square value of the whole current, not just the fundamental component plus all the harmonics. So these quantities can be written as S I1 over Is both root mean square value multiply the cosine of the phase shift. Remember that P over S is the power factor. So now, in that situation, the power factor is given by root mean square value of the fundamental component of the current over the root mean square value of the whole current multiplied the cosine of phi1, the phase shift. Typically, this quantity, which is the ratio I1 RMS over total RMS current, is defined as the distortion factor, KD, distortion factor, while K phi1 is known as K theta, which is the displacement power factor. Okay. Of course, if the current waveform is very distorted, what does it mean? Very distorted means that the root mean square value of the fundamental component is just a minimum fraction of the total root mean square value of the whole current. So this means that I distorted current means that the distortion factor is, let's say, very low. And if the distortion factor is very low, say approaching 0, for example, that means that the power factor is very low. So if you have a huge distortion of the current, okay, you cannot extract all the waveform from the waveform, the total reactive power that you can have in your circuits. Okay, just a minimum fraction of the total reactive power gives you the real power, the useful power. Okay, so it means that, and this happens typically in power circuits. Okay, voltage which is not distorted and current which is distorted. So, for example, I mentioned before about diode rectifier. Diode rectifier are connected to the mains, which you have a voltage Vs, and the voltage Vs can be considered as a first approximation as a pure sine wave, okay? Having, say, Ts period and peak value max. Then you can have diode. Let me consider the classic Gratz bridge rectifier. In this way. And then you have, for example, a resistor R. This is the current IS. What happens to the voltage across the resistor? The voltage here, let me call it VR, is a rectified voltage. Okay, when you have the positive value of the voltage Vs at the input, then you have that this diode here, these two diodes here, let's say the diode number 1 and 4 are on, gives you the same output voltage. Okay, so VR is the same here as Vs maximum, more or less. If I neglect the voltage drop across the diode, should be the same. Then when you are in this situation, so when the voltage at the input is negative, then diode D2 and D3 are on, providing you a expression which is at the output, which has this value. So the frequency here is, let's say, twice the input frequency. What about the current flowing at the output side? The current IR is simply VR over R, so it's something like this. Okay. And the input current is a sine wave, which is Vs over R. Okay, this is IS. So apparently here you have no distortion of the current. Then you can have the total power factor, which is 1, okay, because you have, say, no displacement between the voltage at the input and the current. Okay, they are both sine waves, so no problem. But the problem is that this voltage here is not enough constant to be employed in electronic circuits. So typically what is done is to use here a capacitor. And this capacitor acts as a filter, okay? And so if you use a capacitor as a filter, the output waveform, the output voltage changes totally. Now this is my voltage at the output without the capacitor, but then when you add the capacitor, something like this happens. Okay, so this is with C, and this is without output capacitor filter. So as you can see here, there is a ripple in the output, okay, and it is not constant. You can manage this ripple by, say, playing with the value of the capacitance C, as usual. This is not important here. The thing that you have to understand in this discussion is that now the diodes are just conduct over a very small fraction of the overall period, because the diode now conducts in this small, say, conduction angle, how this typically is called. Okay, the diodes are only here to provide charge to the output capacitor. Okay, increasing the output voltage level. In all the other time intervals, all the diodes are off. Okay, so that means that there is current only due to this small conduction interval. So if you look at the output current, it means that the output current with the capacitor inserted, IR, are just something like this. In this area is a charge, which is the charge provided to the output capacitor to increase the output voltage level. What about the input current? The input current has an expression which is the same of the output current, but let's say with an average value which is null. Okay, so as you can see here now, you have that the voltage at the input is a sine wave, but the current is not a sine wave, it's something which is distorted. In that situation, your power factor is reduced because it only depends on the product of the fundamental Vs, which is just sine wave, and the fundamental component of the current Is. Okay, and so it depends only on the displacement factor that you can have in that circuit due to the presence of some inductances over there. So they are not in phase, the fundamental component at the voltage Vs. So this is a typical situation that can be described with the same parameter I discussed before. Okay, the presence of this current here, the current which is highly distorted due to this mechanism, is something that can be harmful to the operation of equipment and apparatuses that are nearby this rectifier. Okay, because what happens that you can have, first of all, you have to think about that you are absorbing a current from the mains, from your, let's say, electrical fixed source of energy, which has a lot of harmonics. Okay, because this waveform here, if you, let's say, decompose this waveform into Fourier series, you can have fundamental plus a lot of harmonics. And these harmonics are harmful in terms of electromagnetic compatibility, for example. Okay, they can be injected into some other equipment that are connected to the same network. Okay, for example, here you can have another equipment which is totally different from the rectifier powered circuits, which is connected to the same fixed source of energy or electrical mains that has some, let's say, interference due to the fact that you are injecting harmonics, okay, in that network. Another situation is that in order to have a real power, you just have to focus on the fundamental component of the current Is, because this is just the only component of the Fourier expansion of the current that provides you with Vs a real power. But you have a lot of harmonics that do not provide any kind of real power, so they are not useful to provide power to your load, but they circulate in, say, the wires, they circulate into the input ports, and so they circulate, for example, in I don't know, parasitic resistance that you can have here, parasitic inductance due to the wires connecting to the electrical network. And so even though you cannot extract real power from the harmonics, they can, say, eat up these components, they provide, say, malfunction, etc., etc. So this kind of situation happens when electronic engineers start to apply rectifier circuits connected directly to the network, though they are called offline power supply, in order to provide the DC power to their circuits. Okay, with the time goes by, people start to worry about this problem. Okay, so there are some specific commission all over the world that, in order to define a clean electromagnetic environment that made possible to connect several equipment to the same source without injecting or absorbing disturbances and providing less interference and not inducing, let's say, losses into elements due to the harmonics in the network. They try to define some specific rules that you have to accept if you want to sold your equipment on the market, that limits the amount of harmonics you can absorb from power supply. Okay, this is very important. So let me discuss this fact, for example, by just having some a look about what kind of normatives are typically issued to, say, guarantee a clean environment in which you can operate safely your equipment. For example, the CE mark, which is a mandatory mark label that you have to put on your probe that if you want to solve it, for example, in Europe. Okay, and so there are directives that are provided by several committees that involves several different apparatuses. Okay, they define different rules to be followed for different kind of equipment. Okay, so you have, for example, the rules for the medical devices, you have the rules for, let's say, radio and telecommunication equipment, the rules for, let's say, withstand electromagnetic compatibility issues, etc., etc. There are a lot of normatives. One of these directives is the IEC 61003 Part 2, which is directly devoted to the power supply. Okay, the goal is always the same: avoid the generation, the circulation of a lot of harmonics into a common, let's say, supply network. Okay, which is the committee who issues these normatives. In Europe is the International Electrotechnical Commission, the IEC for short, that provides a lot of different topics on this argument. In US, there is the CISPR, the CISP rules, similar directives, maybe with different levels, some different characteristics, and the rules are defined for, let's say, China and Japan, etc., etc. Okay, so this is a table that describes the maximum permissible, admissible harmonics current that you can have in the main supply, for example, for power circuits. Okay, this is the order of the harmonics. For the harmonics number 3, which frequency is 3 times the, say, fundamental frequency, is should have a harmonic current which is less than 2.3 amp. Okay, etc., etc. For each of the order of the harmonics, then you can have a specific limitation of the maximum possible harmonic current. Okay, the goal is to avoid, let's say, this kind of harmful injection of harmonics. Okay, so basically, electronic engineers create the problem. Okay, because they need the DC power for supplying their circuits, and so in order to do that, they put rectifier. But the same electronic engineers that create the problem, they also find a solution. Okay, so let me discuss with you what is the solution that they find out to say, minimize the generation of this harmonics absorption from the source. Okay, so let me share again the whiteboard. Remember, the goal is that I want to get a power factor which is the maximum possible, ideally 1. What does it mean, a power factor which is 1? Power factor which is 1 means that my source, my electrical network, should behave, okay, like a, suppose that there is the rectifier. Okay, there you have the voltage and current, say, extracted from the mains. Okay, then you should have something connected to the output port of the rectifier that make possible to see an input impedance at their input port, which is like a resistance. Because if you have a circuit that acts exactly like a resistance here, then your power factor is 1. Okay, because this situation is the situation that I depicted, for example, here. Oh, it is here, but I had remember these circuits here without the capacitance. Okay, if I do not have this capacitance, then my current is, let's say, this one. So the power factor is exactly 1. So the circuit which is connected to the output port of the rectifier is a resistor. This is a typical situation that I want to replicate in order to get power factor which is 1. So the first thing that I have to understand is that I want to avoid the presence of this capacitance, because this capacitance in conjunction with the rectifier, of course, that induces a short time interval in which the current can flow. Okay, so in order to have just a resistance as a load and OU power factor which is 1, I have to skip this capacitance here. So the first thing that I can have is I want to say succeed in this design, okay, without having too much harmonics absorbed from the supply. I have to avoid the filter capacitance. Okay, and the second is that the circuit connected to the rectifier must operate as a resistor R. Okay, so we need something that absorb here a current which is a sinusoidal current, I in and no B in. This circuit that acts in this way is called power factor corrector, PFC for short. Their action is the power factor correction. Okay, so let me discuss with you what kind of circuits can be employed to, say, operate as a power factor corrector. It's not surprising that the circuits that I show you up to now, so the basic converter topology, the buck boost, or the boost, are good candidates to operate as power factor corrector circuit. Okay, so let me start, for example, with the buck. Okay, so let's try the buck as power factor correctors. Let's try the buck. In order to understand if the buck is can be employed, let me indicate V in and IE on this graph. Okay, if you have, if you accept the fact that the equivalent input impedance of this PFC circuit should be a resistance, then you should accept the fact that the voltage V in is something like this, and the current I in should be something like this. Okay, which is exactly V in over this equivalent resistance. Okay, exactly as it happens for the rectifier with just a resistor at the output. Okay, this is a sine wave. Okay, so this is the input voltage. Okay, what about the level of this input voltage? But it's the rectification of the source. Okay, the source can be in different countries have different levels. In Europe, for example, you have something which is 220 and 220 volt as a peak value. And then you can have to consider the fact that you can have 10% of 220 volt root mean square value, of course. And then plus 10% that you can accept as a nominal variation of this voltage, can give you something like, let's say, 260 more or less volt root mean square value. So the peak value is square to 260, so you can have 360 volt. Okay, more or less. Okay, you can have a better computation, but typically, so the peak value here can be 360 volt here. Okay, this is in Europe. In the US, for example, the peak value can be as high as 130 volts, so can be lower than this, but say 100 volts at the input. What is the basic characteristic of a buck? The buck generates an output voltage which is less than the input voltage. Okay, the buck steps down the input voltage to a lower value. So if you look at the output voltage V0, the output voltage is something which is less than 360. It should be, for example, something like, I don't know, like this. So, as a result of this discussion, is this buck useful as a PFC? Supposing that you are able to control the input current to act, let's say, exactly in this way, so as a resistance. Okay, but this is a totally different discussion. Just as, say, comparing the input voltage and the output voltage. Well, for example, this is the input voltage. I can step down this input voltage from this value to the output voltage. I can step down this voltage to this value here. But what happens here, for example, in this region? In this region with the input voltage is less than the output voltage, this is not a buck. This is not a buck, so my buck operates as intended just in a small fraction of the total period, which is this one. Okay, when the output voltage is, say, when the input voltage is higher than the output voltage. In all other situations which the input voltage is less than the output voltage, this is not possible. Okay, so this means that since you have the operation just in a small fraction of the total period, what does it mean in terms of currents? In terms of currents means that supposing that you have this voltage here as an input voltage and the output voltage is here, so the circuits work as a buck just in this interval here, and so the current, in the case you are, say, able to control the input voltage and the input current to be, say, both sinusoidal, then the current is something like this. E in. So it is good, for example, just in a small interval. And IS, the current as the source, is something like this. Is this a sinusoidal waveform like the voltage Vs? Of course not. You have, say, distortion. So the buck could be a candidate for power factor correction when you, say, I repeat, are able to, say, made a control to make the current I in to exactly be sinusoidal as V in order to have an input resistance here. But as a matter of fact, this is not possible. Okay. Look at what happens for the boost. So let's try the boost. The main characteristic of a boost is that it steps up the input voltage to a higher value. Okay, so this is V in. For example, here, this is T. As I said before, the input voltage can be as higher as 360 volts, for example, so hundreds of volts here in Europe. What is the characteristic of the boost is that the output voltage is higher than the maximum input voltage. So, for example, in that circuit, I can boost this input voltage to this value. I can boost this input voltage to this value. I can boost this input voltage to this value. So, it can operate as a boost for the entire cycle, okay, for the entire duration of T. So, the boost is a very good candidate to become as a PFC, okay, because of course, the output voltage should be higher than the maximum input voltage. And the maximum input voltage, in the worst case situation, you can have 10% more of the nominal 220 root mean square value, should be 360 volt, more or less. Okay? So it means that you have a very huge constant output voltage. Okay? Boost here. We have a rectifier, the main. The output voltage here is very large, higher than 360. So there is the need of another converter placed here, say for example a buck or something like this, to step down this voltage to value that are more easily employed in power circuits. Okay, so you step down this voltage. But anyway, you can use the the boost as a PFC. Two considerations can be made by looking at these graphs. The boost can act as a PFC. Remember that I'm not talking about the control, okay, just talking about the converter. But the PFC can be employed, but you need a specific control action that make possible for the current I in to have a sine waveform in phase with the voltage V in order to emulate an input resistor, okay, in order to get the power factor to be 1. So this is a totally different concept that I don't want to exploit here, okay, but it is possible, okay? They exist, they are sold in the market. They typically, all electronic equipment have a PFC, say, following the rectifier, okay, in order to withstand for the normatives and, say, the regulatory mandatory rules for soldering for your equipment. So there is a control action, which is a huge effort to, say, make this current flowing. So if you look at the current I in should be convinced to follow this path. Okay, in that case, you can have exactly the behavior if you want. The power factor is 1. So two considerations are the following. The first one is that this output voltage V0 is higher than 360. Okay, let's say 400 volt. Here you have a voltage that starts from 0 and then increases up to 360. So suppose that you are in this region here and the voltage is, I don't know, is 40 volt. Just a hypothesis. Okay, there is a point in which the voltage from 0 to 360, which is this value here, reaches 40, or even a lower value, but let's say for hypothesis 40. 40 to 400 means that my conversion ratio should be, let's say, 10. Remember what I said about the duty cycle in boost. You can have a very huge conversion ratio in the boost, or maybe you have some limitations. If you have the conversion ratio, you have something like this. When the duty cycle is 1, okay, you get infinite. But as I said in a previous lecture about the boost, real circuits always have a maximum duty cycle that can be employed around 0.65 or 0.8, something like this. So the maximum possible M is around, I don't know, 4, 5, 6, this number, okay? So you cannot use 10. So how can you make the boost working for this huge conversion ratio that you can have when you say you are in the lowest region of the voltage V? This happens because this can be done because in the situation in which you have a very low input voltage, even the input current is very low. Remember why you get this, let's say, reducing part, this reduction in the conversion ratio M is due to the fact that you have parasitics, okay? And the parasitic gives you for example, the resistance in series with the inductor, gives you a contribution that reduces this fact. Okay, but if you are adopting a boost which is, let's say, designed for very huge power, say 360 volt as an input and maximum, operating at 400 volt as output voltage, no? In the situation in which the current is very low and when the voltage is very low, you are using an over-designed boost for a situation in which the current is very low and the voltage is also very low. So you are designing your boost for a specific, let's say, maximum input voltage, but you have to accept the fact that there is a situation in which your boost is over-designed. For example, when the voltage is very low and the current is very low. In that specific situation, you can reach M, which is 10 or even larger, because all the parasitics you have in your components have a less impact on this curve. So you can, let's say, have a behavior which is, say, can induce a M which is larger, okay, due to the fact that you're using an over-designed boost in a situation in which the current and voltage is very low. Okay, so this can be done not in all the situations, not something that you can do easily. So it's not an advice that is not something that you can do, for example, to over-design always your boost for your application. If you know that your application has as input voltage a DC constant voltage, you don't have to design your boost, you over-design your boost just to have factor M larger, okay? Because in that situation, you are using more expensive components, large components, heavy components, etc. So in that specific situation, if you know that the input voltage is always constant, try to design your boost for that specific situation, not over-design it. But in this case, the boost that should operate for 370 volt, giving you 400 volt at the output, must be used also in the situation in which the input voltage is lower and the input current is lower. So in that situation, you can get M which is large enough. The other consideration is that the input current, as you can see here, is not negative. It's not negative, and the input current is here, but the boost is this circuit here. So it means that the input current flow in the inductance of the boost. So that this means that the boost is operated in CCM. But I always said that pay attention, the boost typically, I said typically, is not operated in CCM due to the difficulty in control it, because it has a right half plane 0 that, let's say, has a bad behavior in terms of stability. So typically it's much easier to operate these in DCM. The magic word here is generally, typically. Okay, this is a situation which you can use the boost in CCM. We can understand why this happens in the following lectures, but just for now, I can use this as in CCM because the bandwidth of my PFC, my boost operating the PFC, is not include the 0 in the right half plane. So since the right half plane 0 at a frequency which is much higher than the bandwidth of my boost employed as a PFC, I can use it in CCM. Okay, something that will be clear later. Well, we have two conditions that we have to understand. Okay, which is the large conversion ratio just for the lower input voltage, and the fact that the boost is operated in CCM. Okay. So this is my boost. This is the output voltage V0, should be DC voltage, larger than the maximum input voltage. Here at the input there is the rectifier, so here the input now is a sine wave. This is a rectified sine wave, something like this. The input current is here. Remember that I have no input filter capacity, so it seems that here you don't have the C-in capacitor, okay? Because the C-in capacitor can act as a filter capacitor C for the rectifier. As I said before, I have to avoid the presence of the input capacitors. Where it is? Okay, here. I have to avoid this capacitor here because it's responsible for, let's say, the distortion of the current. This is also written here, okay? But anyway, in boost, I need these capacitors. So the fact is that this capacitance here is not so huge to act as a filter for the rectifier. So I have this capacitor here, but this capacitor is small. Should be small in order not to act as the rectifier filter. Okay. So the circuit is always the same. So let me derive the output capacitor C0. Okay. So in order to understand which way I can derive the expression of the output capacitor, to design this capacitor, because this derivation follows a different path, a different strategy with respect to a boost, which is operated as a classical DC-DC converter. Okay. Let me draw, for example, the input power. I have this is Vs, and then I have the current, okay, Is. Sorry, I call as V in and I in, okay? So which is the power? The power is the product of the two. The power entering the system, so the power which P in, if you want to call it this way, is null here, is null here, is null here, etc. Okay, and then it has a maximum here, so it's something like this. Let me draw this graph here. This is the input power. This is T, which is the original frequency of the mains, which is, by the way, 50 Hertz in Europe, 60 Hertz in US, for example, so low frequency. And this is T divided by 2. So the frequency of the power is twice the frequency of the mains. So 100 Hertz in Europe, 120 Hertz in the US, etc., etc. The output power is something which is constant. Okay, the output power P0 is constant. It's constant because it's the power given as the product of the voltage V0 multiplied the current I0, which is our DC quantities. Basically, if we consider the circuits, say lossless circuits, that the average power of the input is the output power. Okay, so the average power of the input is the P0 power. And the average power of the input is something which is, say, here. Okay, so this is P0, which is the output power. So as you can see here, there is a time interval in which you have large power than the output average power. There is another interval here in which you have an input power which is less than the output average power. So there is a time interval in which you are, say, have an excess of power, okay? And so the excess of power should be stored somewhere in the circuits, okay? And then you have a time interval in which you have, say, missing power. And so that means that at the output port, in order to have the power constant, the energy which was previously stored should be released to the load in order to have constant power. So, which are the elements that inside the boost can act as a storage element? Okay, if you look at the circuit, scene is very small, as I said before, because it don't want you, let's say, have an excessive loading effect in the rectifier. So you want to put a filtering action at the output of the rectifier to avoid distortion of the current. Can store this energy into the inductance, but the inductance is designed to different for different scopes. Okay, meaning that the only elements that can store this energy and that can release the energy alternatively in a period is the output capacitor C naught. Okay, so it's C naught that in this time interval here take this excess energy and stored into the electric field across it, and it's the same capacitor C naught that release the previous energy to, say, fill the missing of energy in the green time interval, as I show you here, in order to maintain the output voltage constant. Okay. So suppose that you have this kind of behavior of the input power, as I shown you, which is something which is here, in which this is the average. Okay. P naught. The frequency here now is 2 times the input frequency. So there is a time interval which is in which the input power is in excess. And what happens when you provide to a capacitor energy to be stored? Okay, the area under here is an energy. When you provide to a capacitor an energy, you are providing charges that make possible to vary the voltage across this capacitor. Okay, so if you have a capacitor and then you provide energy, then you are increasing the voltage across it. In the same way, when this capacitor releases the energy, and this happens here in this interval, so the voltage across this capacitor reduces. Okay, so if the fact that the energy can be positive or negative has a direct implication about the voltage variation across the output capacitor. So look at what happens to the output voltage. The output voltage has an average value, which is V naught. But then what happens in this interval? Look at the interval in which the energy is provided to be stored into the output capacitor C naught. But in that situation, I have an increase in the voltage. So if you look at the output voltage, in this interval, you have something like this. Let me change the color. Okay. During this time interval, the voltage increases due to the excess of energy provided to the C naught capacitor. In this time interval in which the C naught capacitor, say, release this energy, then the voltage across it reduces. So you have something like this. You have a ripple across the output capacitor, delta V naught. The ripple has a frequency, and the frequency of this ripple is exactly two times F. So if the input frequency is 50 Hz, you can have 100 Hz at the output. Okay, so very low frequency. Of course, this capacitor has always the ripple due to its ESR. Remember, the ESR gives you the ripple at the switching frequency. The switching frequency can be much higher, can be 100 kHz. So there are simultaneously two kinds of ripples. One is due to the switching frequency and the ESR, for example, giving you 100 kHz, for example, switching output ripple. And then another ripple due to the mechanism of operation of this PFC boost, which is a ripple delta V naught, which is a very low frequency, 2 times the input mains frequency. So delta E is the energy that I can provide. This energy in a capacitor is 1/2 C naught for the delta voltage square. So that means that is 1/2 C naught, supposing that this value is V naught minimum and this is V naught maximum. So I have V naught maximum minus V naught minimum square value. Okay. There is another way to write the same expression. Delta E is 1/2 C naught V naught max plus V naught minimum and V naught max minus V naught minimum. Okay, it's the same expression as before. But now I can recognize that VO max minus VO minimum is the delta V naught, is the ripple. While VO max plus V naught minimum divided by 2 is the average output voltage, is V average value. So the voltage I can have at the output. So it's V naught the average value. So it is V naught. So that means that I can write that delta E is CO delta V multiplied V naught. This energy is the energy which is provided to the capacitor that is possible to increase the voltage. Okay, is the energy which is provided here from VO minimum to VO maximum. Okay, delta V is exactly given by this expression. This energy is the area under this sine wave. Which is the area of this sine wave? The area of this sine wave is given by an expression which is similar to that of a parabolic area. Remember that for a parabolic area, we get something like 2/3 and the base and the 1/8. Okay, something like this. This is a parabolic area, and this is the base, and this is the 1/8. So the rectangle that encloses 2/3. For the sine waves, this term here is a little bit too much. And when you always have sine waves, typically you get P as a number. So is the 2P multiplication of the base and the 1/8 of a rectangle that encloses it. Oh, this is P naught. The peak value is 2P naught of this power. So the difference here is exactly P naught. So P naught is the 1/8 of this rectangle. The base is half the period of this power, but the period of this power is T divided by 2. So this quantity is T divided by 4. So the energy, which is computed on the graph of the power, is 2 divided P, the 1/8 is P naught, and then you have the base. Now you can equate these two expressions, and if you can equate these two expressions, you can find that C is equal to the average power P naught over 2P, the frequency at the input, V naught average value, the admissible delta V naught. Okay, this is the way I can define the output capacitor C. Why in this way, in this case, I have to define the value? Remember that when I talked about the C naught capacitor in the boost, I said this is not very important, or in the back, it's not so important the value of the output capacitor. It's much more important the ESR of the output capacitor, because it is the ESR that induces the switching ripple at the output. So when in the problems, even the problems that I assigned at the beginning of this lecture about the buck boost, that the output voltage ripple should be less than, let's say, 100 millivolt, that means that you have to design the ESR of the output capacitor, not the value of the output capacitor. But this is due to the fact that the ripple that I'm talking to you in classical standard topology of the boost buck boost is the ripple at the switching frequency. And the switching frequency is, let's say, 100 kilohertz, 200 kilohertz, 500 kilohertz, in a region of frequency in which the electrolytical output capacitor is no more a capacitor, is a resistor. Remember, it acts like a resistor, which is called ESR, because the switching frequency is large. Now I'm talking about a ripple which comes out at a frequency which are well lower than, let's say, the switching frequency. It's 2 times f, which is, I don't know, 10 hertz or 100 hertz or 120 hertz in US. So there are, let's say, several order of magnitude less than the switching frequency. At 100 hertz, this ripple, okay, the output capacitor C0 is still a capacitor. It's not a ESR. No, the mechanism by inducing this ripple is totally different at different frequency. And so in that case, I need to define the value of the capacitor, and I show you a procedure to define this capacitance, just because we are a frequency f, which is, let's say, 60 hertz or 50 hertz in Europe. Sometimes you have 100 hertz, 400 hertz in industrial application, airplanes, etc. But anyway, is very, very small. So now I can answer the 2 questions. Okay, Simonetti Mark, can you repeat what happens back when Vin is less than VO? When Vin is less than VO, the buck is no more a buck, because the buck always has Vin higher than VO. So this means that typically you don't have any current flowing through it. The two switches, the diode and the MOSFET, are left open. Okay, in that situation. And so if you have both open, it means that you have no current flowing in the input side. So the current is null in that time interval in which you cannot have the buck operation. Okay, the buck is defined this way only when your input voltage is higher than the output voltage. If this is not happens, both the switches are open, no current can flow in the buck. Miss Kali, can you repeat why we are in CCM? We are in CCM because the current that is showing this slide, as you can see here, the current IL, okay, in the inductor is the current that flows here. The current that can be convinced by a specific control action to follow a sinusoidal path at the same frequency with the voltage PS. In this case, it's called PS. Okay, but this is the current flowing in the input side of the boost, is the current flowing in the inductor, and is a definition that a circuit is in CCM or in DCM depending if the current in the inductor is totally positive or can have some period, some interval in which is negative, okay, or null. So since the current here is, let's say, null, just 1 point, we can say that we are operating the critical mode if you want, but of course this is not in DCM. DCM means that the current IL should be 0 for a short time interval, the idle T3 time interval. This is not the case. The current is always positive or can be 0 at just 1 point. So you are operating in the critical mode or in CCM. Okay, so this is why. It's definition. You have to look to the current flowing to the inductor. If the current is totally positive, CCM. If the current is, let's say, as a period in which is null, is DCM. In between, you have a critical conduction mode. So, sorry for delaying my discussion. Okay, I can have just a little short talk at the beginning of the Monday lecture. Okay, but then we can start. We can continue talking about the control. Today, 2:30 p.m. there is the laboratory. Okay.